welcome to our Digital Futures Saturday tutorial series. We're very happy to have you all. My name is Reem and I'm a part of the Digital Futures World team. Today, our session is going to be on Introduction to Genetic Algorithms in Grasshopper, hosted by our instructor, Sorial. But before we begin the session, I'd like to take the chance and announce some of our upcoming Digital Futures World sessions and events. So this month, we're going to have one of our first Italian Talks session hosted by our Italian channel. The session is titled as New Hybridities, and the session holds many of the expertise in the fields of computational design, AI, material fabrication, and different fields. We'll be having guests such as Angelica Lorenzi from CIARC, Gabriella Rossi from CIEE, Valeria Piccioni from ATH, Antonio Benarchi from Eros SOA, Alessandro Somparelli from STU Create, and finally Nicholas Turkey from NETR. Another upcoming session is next Saturday. We'll begin with our series on tutorials on AI and Midjourney, where we'll have our first theory session hosted by Professor Neil Leach. So keep an eye on that and follow us to check on our events on Instagram. So let's go back to our tutorial. So I'm happy and it's my pleasure to introduce you today, Danielle Sorial, our instructor. So Danielle is an architect and a computational designer. He has obtained his master's degree in Advanced Architecture from IAAC in Barcelona. He's currently teaching in the Future Studio in CIEE at IAAC. He's also working as a computational designer at External Reference. Daniel's research focuses on an interesting merger between algorithmic designs and neuroscience. He's specifically studying the effect of geometric behavior on the user's cognitive emotional interaction. So we're very happy to have all the students here today. Our tutorial is going to take you through a complete workflow from the design process to environmental analysis and supported by generative optimization, where you're going to learn the workflow of using Grasshopper in the design process, as well as the key concepts for environmental analysis and multi-objective optimization. And finally, you're going to learn how to set up a generative optimization process. So just want to announce that thank you for everyone who's joining us here today on Zoom and YouTube. We're going to be having our Q&A session at the end, so make sure to drop all your questions in the chats or on the comments on YouTube. So welcome, Danielle. We're happy to have you here with us today. I'm going to leave the screen and the mic for you.
Thank you, Reem, so much for the introduction. Hello, everyone. I'm going to share my screen right now. Okay, can you see my screen?
Yes.
Okay, perfect. Okay. Hello, everyone. So today we're going to talk a little bit about introduction to genetic algorithms in Grasshopper. Of course, the genetic optimization is a huge topic in general. We're not going to be able to cover everything for sure, but we're only going to cover a little bit of introduction with a focus more on the workflow rather than the design itself, right? So the aim of this this tutorial is actually to design a workflow that starts from a basic design that we're gonna basic script that we're gonna design, and then we're gonna do a little bit of analysis, how to analyze the design that we created, and then moving on to how to optimize this this design based on those objectives. So just I'm going to share like a couple of slides. It's not that much. This is just an overview of how this workflow works, right? So first we start with a design, and we specify design variables. Like if I'm designing a box, you have the size, rotation, scale, and so on. So those are the design parameters, and those in the terms of genetic optimization usually is called genome. Okay, and then after this, we move on to analysis or the objectives, and this is how we analyze the design we created, whether it's environmental analysis or geometrical or spatial analysis. It's up to you basically. What are the analysis and what are the objectives of the design, right? And it's called fitness. This is the again the term that is used in the plugins that we're going to be using. So in terms of environmental, whether it's the amount of sunlight, the amount of direct radiation, diffuse radiation, amount of shade and shadow, whatever environmental analysis that could be, or if you want to check against geometrical or spatial, whether it's the volume, the area of the space designing, or maybe the amount of view that is exposed to either an object or like the surrounding. So of course, those are just examples. You can specify whatever analysis that you are looking for. And then the third part, which is the optimization part, which is we're going to be using genetic solver. There are different types of solvers. There's single objective solver and multi-objective solver. Those are the most common solvers. And we're going to be using Galapagos, which is a native solver in Grasshopper. And we'll talk more about the solvers later on through the session. So this is how optimization works. We have a design that has variables, and then we test those variables against an objective, and then we feed this objectives to the solver, right? And then the solver analyzes this objective and then goes back and changes the design parameters, and this loop keeps on happening until we have the best objective. This is basically the algorithm works. So this is an overview of the tutorial that we're going to be working on. I'm going to run this video real quickly, and then I'm going to pause in the middle and explain a little bit everything. So we're going to have an area that has a grid, and then we're going to divide this grid based on curves. And then we're going to start building up those grid divisions into a block pieces, right? And then we're going to control how this, let's say, neighborhood or this urban plot is being extruded. And then we'll control also the scaling of it, right? And then we're going to analyze this against specific fitnesses. So sorry. Okay, so this is the process that we're going to go through. We're going to define an area that we're going to work on. Then we're going to generate curves. Okay, and then we'll add a specific behavior to this curve, right? So we're going to say that whenever there is an intersection between the curve and the grid, I want to subdivide this grid even more. So, and whenever there's more intersection, I'm going to subdivide this grid even more. So it's like I'm creating hierarchy within the grid for bigger plots to be used for a specific purpose, and then the smaller the plot I get, the different purposes that or the different functions that I can be using throughout, right? So this is how we're going to construct the design. Then we're going to move forward to have two different behaviors in this design that we're going to have. The first one on the left is the number of floors for each plot, right? So we want to be able to control how many floors we have in each plot, in each of those buildings. But we also want to control how much area, how many percentage is being taken from the total plot, right? So maybe as you can see here on the right, some of the buildings can be occupying the full plot, and some of them can be offsetted inwards. So here we're controlling also the scale of those buildings. So those are the two behaviors that we're looking for. So the objectives that we're looking for are three things. So again, we start with the design. Design variables are number of floors, location of plots to scale, because we don't want to be scaling all the plots together, right? We want to be scaling specific plots, and I'm going to explain why. And then we're going to work on the value of the scaling, or what is the number of the offsetted value of each of those plots. We're going to move on to the analysis. So the goals that we're trying to have, we have an environmental goal and we have a geometric or a spatial goal, right? So the environmental goal is we want to minimize the amount of radiation on the buildings. And we also want to maximize the shade for the public space. So if you go back, you're going to see that we have here two public spaces inside this, this urban area. And we want to maximize the shade within this urban plot, right? But we also want to minimize the amount of radiation exposed to all the buildings. But we also have another objective, which is a geometrical objective. We want to have also the maximum total built-up area for the buildings, right? So we want to maximize the total built-up area, maximize the shade in the public spaces, and minimize the amount of radiation. So working with genetic solvers is actually you're giving it an equation, and the genetic solver is trying to solve this equation based on the inputs or the goals that we're trying to achieve, right? And some equations can be pretty simple, pretty straightforward, but when multiple objectives like this one, the equation gets a little bit complicated and gets a little bit tough. And this is why we use genetic solvers to actually solve this equations. And then we feed this again to the optimization to have the Galapagos. We're going to come back to this later. Okay. I'm going to start now the Rhino file, and we're going to start building up the script. So it's important to understand something, that this part of the tutorial that we're going to do is actually pretty flexible. So what we're trying to do here is we want to generate the full workflow. You can essentially replace this part of the design with whatever design you want. There are multiple of YouTube tutorials on different designs that you can use, but if you want to have the same workflow, then regardless of the type of design that you're going to have here, it's also going to follow the same workflow. And this is what is really important about this tutorial, which is to teach the workflow regardless of the design that you're going to have. Okay. So as stated, we're going to start first with specifying an area, and then we're going to generate certain curves. Maybe those curves are the roads, the streets, or maybe the boundaries of the plots. And then we're going to start generating the grid, dividing the grid, and then extruding the buildings. So first off, we're just going to start with defining an area. So I'm going to go to Grasshopper. Sorry, go to Rhino preview, and then I'm going to click on rectangle, and then I'm going to specify a rectangle. Okay. So the way Grasshopper works, I'm also going to be covering a little bit of like basic knowledge about Grasshopper. So sometimes it's going to be a little bit boring to know some of the information that some of you might know, right? So Grasshopper works as an interface inside Rhino, right? So whatever happens in Grasshopper, it will always in Rhino, right? So in order to link something that is on Rhino into Grasshopper, we need to use one of those parameters to link it. So first of all, I'm going to double click and type curve. Okay. In order to link something on Rhino inside Grasshopper, you right-click on the parameter, and then you click Set One Curve, and then I'm going to select this curve. Okay, so this is the first step, which is specifying the boundary, right? Then I want to start creating a grid. So in order to create a grid inside a curve, I'm going to first use boundary surface to transform this curve into a surface, okay? Again, Grasshopper works with input and output. So you need to always connect the output of the component to the input of another component. Okay, so starts with the curves. We go to a surface, and then we want to use something called isotrim. So what isotrim does is it extracts an isoparametric subset of a surface, right? So if you ever face a difficulty understanding which part of which component does what, you can easily just right click on any of the components. You can click on the help, and then it's going to explain to you what is exactly this component doing, and it's also going to give you what are the inputs expected and what is the outputs to be expected, right? So, and as an input, it needs a surface, right? And then it needs a domain. So I'm going to connect the surface with the surface, okay? And then in the domain, I'm going to type divide domain, and then I'm going to pick divide domain part 2, which it divides a two-dimensional domain, right? So in a U and a V count. So in order to divide this surface, I'm going to connect the domain, which is the start, the base domain of the surface, and then I'm going to have 2 in the U count. And then I'm going to copy this. I'm going to connect to the V count. Okay. Then I'm going to connect segments to the domain. And once I do this, you're going to see here that the surface is divided into 2 parts. If you're seeing this overlapping in visuals, this means that you need to hide the previous components. In order to do that, either click on the component, right click, and preview on and preview off, or you can select the components and you can click middle mouse button, and then you can see here that this is enable preview and this is disable preview. So you can disable the preview, or on your keyboard you can type Control Q. Okay, so this is the first step. And if I want to increase the number of division, I can increase it by the U or the V count. Since I'm using a grid, I don't think I need to have two different sliders. So I'm just going to connect one slider to both, and I'm going to keep it at 3. Then I'm going to delete this one. Okay, so what I want to have now, if you go back to the presentation, we have the grid, but we also need to generate the curves, right? Where the grid is going to be more subdivided. So I'm going to go back to the Grasshopper, and then let's draw 2 different curves. I'm going to draw a curve like this, maybe another curve like this, right? And then I'm going to link those curves. So I'm going to type in curve, then right click. And since I want 2 different curves, I'm going to select set multiple curves. And then I'm going to select and 2, and then I'm going to click enter. Okay. So what I want to have now, it's something called condition. So I want to set in a condition where whenever this curve intersects with a subsurface, I want this subsurface to be divided into more subdivisions. Okay. So in order to do that, you can see here that the output of the isotrim is actually the 9 surfaces. And to visualize the data, you can type in panel and connect the surface to the panel, and this will visualize the data inside a component. So here we have 9 different panels, and if you want to select any of those, you can just click on list item, connect this here, and then you can see that we highlighted the first one, and then we can create a number slider from 0 to 9. And then if I move this, I'm selecting different subsurfaces. Okay. So what I want to do now, I want to create a condition. I want to say whenever there is an intersection between the curve and the surface, I want to subdivide the surface even more. Okay. In order to do this, I'm going to type collision, and I'm going to do collision 1 to many. Okay. So again, if you do not know what is the component, you can right click, type on help, and then it'll explain. So this test for one, so test one object against many collisions, right? And it needs two different inputs. One is the collider, which is the objects for collision, and one is the obstacles, right? What is this object hitting? So what I'm gonna do is the collider is going to be surfaces, and the obstacle is going to be the curves. Okay. So you're going to see that the output here is a true or false. Okay. And this is what's called a Boolean output, right? So a Boolean output is actually gives you a true. If the collision occurred, then it's a true. If the collision did not occur, it's a false. And you can clearly see that I have only two subsurfaces that are not colliding with those two curves, which here you can see that we have only two that are false. So in order to use this collision, I'm going to use something called dispatch. And what dispatch does is it actually splits a certain list into two different lists, list A and B, based on a pattern. And this pattern is defined by a true or false. So if I connect the collision to the dispatch pattern and I connect the surface to the list, I'm going to have two different outputs. I'm going to type in surface, and then I'm going to connect list A, which is going to give me this U shape. Again, if you can't visualize the last thing, maybe you need to hide the rest. So all that is true is going to be moved into list A, and all that is false is going to be moved into list B. So I'm going to have two different surfaces. One is for A and one is for B. Okay. Then I'm specifying that I want all the surfaces that I have from list A to be subdivided even more. In order to do this, I'm going to again repeat the same process that has happened here, right? So I'm going to do isotrim, connect this surface to this surface, and then I'm going to do divide domain again. And let's say that this time I'm going to do it 2. I'm going to connect the 2 to the U and the V counts. Okay, in order to give a little bit of hierarchy to the to your scripts, it's useful to change the names of the components so that it's easier to identify, right? So in this surface, I'm going to right click here, and instead of surface, I'm going to type grid A. And then I'm going to use this application setting right here, click on it so that it changes it from an icon to the name that I specified. Okay, so this is grid A, and then actually I'm going to specify this later. So then I'm going to connect the segments to the domain, right? Because this is what we did earlier before. But then what happened here is it gave me a little bit of an error. And you can clearly see that the surfaces that I've created here are not actually subdivided as I'm looking for. And this is because the data management is not matched correctly between the components. So I'm going to get a param viewer, and then I'm going to copy paste it. And then I'm going to connect the surface to this one, and then I'm going to connect the segments to this param viewer. So data management or data matching in Grasshopper is actually the heart and core of Grasshopper. It's one of the most difficult topics that you're going to be exposed to in Grasshopper, but also it's what makes Grasshopper, essentially. So in order to do this, we have here two different sets of data, and each differently. So we understand that in this surface, in this component here, we have a list. This list contains 7 different services. While if I click here, type panel, and then connect to the segments, you're going to see that it's structured differently. It has 7 different branches, and each branch has 4 different components. So if I double click here, I'm going to visualize this is how the data is structured. So data is either structured by tree with one branch, tree with multiple branch, and then each branch contains items at the end of those branches. So what is happening right now is that it's connecting the first surface to the first data, and then the second one to the second data, and it's messing it up because the data are not matching. So what we want to do is we want to have 7 different branches, like here, have 7 different branches, so that each branch will be divided into 4 different surfaces. So in order to do this, we use something called graph. So what I'm going to do is I'm going to connect this to the graph tree. And when I do this, this will happen. So if I take a copy, take a look at this, well, what is going to happen here is that it's going to take each of those surfaces, the 7 surfaces that we have, and put each one on a different branch on its own, right? And then if I actually connect this tree to the domain and to the surface, you're going to see that the surfaces are subdivided equally. Because now what I have, is each branch is corresponding to the other branch. So this means that the first branch here, which is the first surface, this surface is being divided into 4 different surfaces. And then we're going to the branch number 2, and then this branch is going to be subdivided into 4 different surfaces, and so on. Okay. So what I want to do is I want to keep doing this maybe one more time. So I'm actually going to do, again, a collision. One too many. And then surfaces are going to be the collider, and the obstacles, I'm going to go back and use the same curve that I used before as the obstacles. And then I'm going to do a dispatch, connect the collision to the dispatch pattern, then connect the surface to the list. Then I'm going to type in surface again, connect list A to the surface, and then you're going to see that only the surfaces that are colliding with the curve are being selected. Then I'm going to hide the rest again. I'm going to copy this, connect it to the second surface. Now I'm controlling each set of surfaces, right? And then maybe I want to subdivide this one last time. So again, I'm going to do isotrim, connect the surface to the isotrim, then graph this, type in divide domain, again type in 2, connect it to the segments, and there you have it. You can essentially increase the number of subdivision, and it will update the script. Okay. Then let's say I want to again use the collision one last time, connect the surface to the collider with the obstacle, and then use the dispatch again, connect the surface, and then connect this to collision so that I can actually control those surfaces. So I can select the surface on the line and the surfaces that are not on the line. Then I'm going to hide everything that I'm not looking for. So this is grid A that we have. This is grid B. And this is grid C. And right click and grid D. So What we can do now is, if I actually move this curve, you're going to see that the points, like all the subdivision, are going to be updated with the script. This is one of the strongest things about actually Grasshopper, is that having this parametric workflow that you can actually control, change at any point one of the main inputs, and then everything is going to update. Okay, so let's go back to the script. So we defined the area, we generated the curves, generated the grid, and we subdivided the grid into smaller parts. What we're looking for now is we want to generate those buildings on those grids. Okay, so I'm going to go back, and then I'm going to use grid D, which is the last part, and then I want to create floors. So what I'm going to do is I'm going to do move, and then I'm going to connect this geometry to this geometry. So if I connect the grids that I have right here to the geometry, all is going to move up in the Z direction, because sometimes when we don't have an input value, some of the components, they have default values, which is right here is 0, 0, and 10. Okay, so what I want to do is I want to have this to be moved in the Z direction, which is correct, but I don't want it to be moved just one step. I want to create multiple floors. Okay, so I'm going to type in unit Z, and then I'm going to type in 3 as a factor. I'm going to connect this here, and then I'm going to connect it to the motion. So if I move this, all of the surfaces are going to move within the same value, right? But it's also going to be only one floor created, right? However, if I created different sliders, copy paste, different sliders, and then while holding shift, I connect those sliders together, you're going to see that now I can control different heights. And instead of moving this grid only one time in the Z direction, I can be able to move it multiple times. So right now, you're going to see that I have 1, 2, 3, 4, which are 4 floors, because I have here 4 different values. Okay, so if I actually merge this, and take a look at the result, I'm creating a list of 4 different values, and then I'm feeding those different values to the factor. So it's creating each of those geometry, which is the grids here. I'm moving it in the Z direction with those 4 different values. Okay, so if I want to generate, let's say, 15 floors, then this means that I need to essentially copy this 15 times, which is unrealistic. So there are multiple ways to generate this. One of which is called series. And what series does is it creates a series of numbers, right? So it creates a number that starts from 0, and it has a step, and it has a count. So I'm going to connect this to the panel, and let's see. So first thing, it will ask you, what is the start of the series, right? So let's say that the start, we want the ground floor to be on the ground. So we want the first value to be 0, right? And then the step, which is the height of the floor, let's say it's going to be 3. And the count is essentially how many floors do we have. So if I type in 11 and put it in the count, this means that I'm generating here a list of different heights, 0, 3, 6, 9, and so on until it reaches 11 floors. If I connect this series to the factor, I'm already going to have this type of behavior, right? And then I can control this by increasing or decreasing the number of the distance between each of those steps, or the number of floors we can have, right? But if I want to control each of those buildings on their own and not actually controlling all of them together, then this means that I need to generate a set of number sliders for each of those buildings on their own. So let's go back to check the data in the surface. So right here we have the surface, and if you take a look, we have different trimmed surface, untrimmed surfaces, and they're all listed, each one like branched together in different branches. Okay, so what we want to do is we want each of them to be on a branch on its own. So I'm going to right click and then I'm going to graft. And when I graft, then this means that each of those surfaces, each one of those surfaces are going to be on a branch on its own. So this means that I can generate different heights on their own. So what I'm going to do is actually we're going to use something called gene pool. And it's one of the things that we use a lot with genetic optimization with Galapagos. So what gene pool does is it actually generates list of number sliders inside one component. So instead of copying this multiple times, you can just create the gene pool. In order to control the gene pool, you can right click on the gene pool and then you can click on edit. And then you can specify how many sliders do we want, what is the decimal of those sliders, and what is the minimum and maximum values of the slider, right? So this one goes from 0 to 100, and we have 10 sliders. So in order to know how many sliders do we want, this means that we want to have as many buildings as we have here, right? So if you hover the cursor over the component, the grid D that we have, you're going to see that this component has 29 different values. You can also check this by tree statistics, connect this here, and then generate a panel to the count, and it's going to tell you that there are 29 different trees, 29 different branches inside this component, which means we have 29 different buildings, right? So what I want to do is I want to generate here 29 different sliders, right? So I'm going to go here, then I'm going to type 29 in the gene count, okay? And then what I'm going to do is, instead of having one slider in this series that controls all the buildings by the count, I want to generate different sliders in the count. I'm going to delete this. Okay, so if I change the count up and down, this means that all of the buildings are moving with the floors up and down. But if I want to control each one on its own, I need to create different number of sliders, right? So I'm going to do the same. I'm going to use Shift, and then I'm going to connect all this to the count right here, right? And then if I increase one value, you're going to see that only one is being increased, right? And then the rest is going to be connected to the last one. So this means that if I want to control each of those buildings to be moved separately, this means that I need to have this amount of sliders, right? Which is the 29 that we saw here. So again, with the gene pool, I'm going to right click on edit, and then I'm going to say that the minimum height that I want is going to be 5 floors. And then the maximum is going to be, let's say, 20 floors. Okay. Then instead of connecting those sliders to the count, I'm actually going to connect this gene pool to the count. One of the interesting things about the gene pool is that you can right click and you can randomize the values of the gene pool. And when you randomize, you can see that each of those buildings are now being controlled separately on their own by the number of floors each of them have. Okay, so I'm going to go back. I'm going to change this. Maybe 20 is a little bit too much. So let's say 15. Enter. Okay, so now that I created the different floors, I want to actually generate the building itself. Okay, so in order to do this, I'm going to extrude this geometry. So right now we have this paper thin buildings, but we want to create a volume, right? So I want to create a volume out of each of those floors. So I'm going to extrude each of those surfaces in the z direction, and I want the distance of this extrusion to be equal to the floor height. So since right here, this is the step of each of those slabs, so I'm going to write here, I'm going to type in floor height, and then I'm going to connect this to the factor here. So you're going to see that this is being perfectly extruded. And moving forward, I'm just going to use a simple mesh and connect it to the vrep. Then I'm going to hide it. So we have here the meshes. So using Galapagos, and also while using Ladybug as an environmental analysis plugin, it's a long process, and it takes a lot of computing power. So sometimes you need to reduce or manipulate the script a little bit so that it takes less computing power, so that the script would be faster. Some of the optimization process can take up to days and weeks. It can be an unending process. So it's really important to simplify the script as much as possible while working. And using meshes is actually one of the easiest and fastest ways. Not generally, but in this case, it's super fast to create a simple mesh and then use it to analyze the buildings. Okay. So using the same process that happened here, I can essentially go to grid C, and I can do the same thing, and I can actually build different type of buildings around each of the grids. Right now, I'm just going to use the one that we already built, and then I'm going to move on to the Ladybug environmental analysis so that we can see what is being affected and how to control it. Again, if at any point I want to move those curves or control them, you're going to see that the whole script is going to, again, adapt to it. Okay. So moving on, now that we generated the grid, I'm actually going to go back, and probably I'm going to change this into 3. And maybe change this to 3. I want to have different control over the grids. Okay, and maybe okay. Okay, so moving on, the next part is going to be the Ladybug, which is the analysis that we're going to do on this design, right? So let's go back and check the script. So in the presentation, we said that we want to control 2 different things. The first one, which is controlling the heights, and we're already controlling the heights. The second thing, which we need to do right now, is actually control the different scaling of those buildings, right? So before jumping into Ladybug, let's generate this part. So this means that we want, I'm going to hide this for now. So this means that those grids that we have here, we want to be able to offset this grid inside, right? So I'm going to type in offset. Then I'm going to connect this grid to the curve. And as you can see, the offset is being offsetted outwards, and we want actually the offset to be inwards. right? So I'm going to go in here, and then I'm going to type a distance of, let's say 1. And then instead of the distance being positive, which is being offset outwards, I'm going to type in negative. And then I'm going to connect negative to the result. And then you can see that the offset now is being offsetted inwards. And then I can control the value of the offset. So again, now we're controlling the offset of all of them, okay? But I want to do something different. I don't want to generate different offsets based on a random value, because we can generate random offset values, but I wanted it to be changed based on proximity. And this was one of the goals that we have here. So if you take a look at this one, you're going to see in the GIF that wherever there is a point with a circle, the buildings closer to this point are actually smaller to the buildings that are furthest away from this point, okay? So this is a workflow that is called attractors in Grasshopper, and it's pretty useful. So I want to introduce attractor to this script. So I want to create different points, and I want to say whenever there is, whenever the point is closer to a building, I want to be able to scale this building or offset this building, okay? So I'm going to go back. In order to do this, I'm going to go back to the surface that we created, which is the big surface that we created here, the whole plot. And I'm going to type in surface, connect this surface here, and then I'm just going to move it there. So what I want to do is I'm going to type in evaluate surface. And then I'm going to connect the surface to the surface. And then in order to get a point, I'm going to type in MD slider. And then I'm going to connect the point to the MD slider. And then I'm going to start moving this point. And when I do this, you're going to see here that the point that is appearing here is actually moving, right? But it's only moving in one grid, right? So it goes from 0, 0 to 1, 1, right? Because it's moving in, it's using it as a unit, right? So 0, 0, and this is 1, 1. But I don't want the point to be moving this way, because if it's only like this, I need to actually double click and check the actual length and width of the surface and then add it here. So if I type in 12 and then keep moving, then the motion range of this point is going to be larger, but it's also not going to be able to cover the whole surface. So what we usually do is we keep it from 0 to 1, and then there's a trick in Grasshopper when you right click on the surface called reparameterize. What reparameterize does is it actually assumes that 0, 0 is the start of the surface and 1, 1 is the end of the surface, right? And if you go in 0.5 and 0.5, this means that it's going to be the midpoint of the surface. So it scales in the surface regardless of the actual dimensions of the surface to actually be considered as if it's a ratio. So this is 0, 1, and 0.5, and then you can move freely on the surface, okay? So what I want to do is I want to create proximity. So I want to say, actually, I want to connect this point to the center of those plots. So in order to do this, I'm going to type in curve, and then I'm going to connect this grid to the curve. So now I can select those plots. And then I'm going to, in order to get the center point of those curves, you can just type in area, and then you connect geometry to the area, and then the second output of the area is actually the centroids. So what I want to do is, if I create a line between the centroids and the point, this will happen, right? So this is the proximity that we have. So whenever the point moves, it generates a line. And I want to specify that the shorter the line, the more offset we do, right? So this is the condition that we're creating. So in order to do this, I'm going to type in distance so that we can actually calculate the distance between the centroids and the points. And then I'm going to check in the data, and then we're going to see here that there are a list of different distances, right? So what I want to do is I want to create, again, a ratio, right? So I know that, for instance, here there's a distance of 70 meters, right? So I want to say, this actually, I'm going to type in bounds. So what bounds does is it gets you the minimum and maximum values of a set of lists, right? So I want to know what is the closest distance, what is the shortest distance, and what is the furthest distance. Okay, so I'm going to connect this here, and then I'm going to flatten this list, and then I'm going to connect it to a panel. So this shows me that the distance are from 11 meters to 75 meters, right? So if you take a look here, this means that probably this point is the closest point to the point that we generated, right? And this is the furthest. So what I want to do is I want to create a sort of an equation. I want to say whenever you find the value is 11, I want the offset value to be something, right? So let's do this. So I'm going to type in remap numbers. So what remap does is it takes a set of values, takes a set of numbers, right? That has a domain, a source, which is in this case from 11 to 75, and then it changes this domain to a different domain, okay? So what I want to do is I want to make the smallest value, the smallest distance that we have here, which is the 11 value, to be offsetting the plot 1.5 meters, right? While the largest distance, which is the 75, I don't want to be affecting the offset, so the offset should be 0. So in order to do this, I'm going to connect the distance as values. And then it's going to ask you here for a source of the domain. So what are the source? What is the minimum and maximum values of the list that we just connected, which is the bounds that we created here. So I'm going to connect this here. And then it's going to ask you, okay, so what is now the target domain? So what is the minimum and maximum, the newly created minimum and maximum values that you want this, this list of values to be adapted to? So in order to do this, I'm going to do a construct domain. And then I'm going to connect the target to the domain. And then I'm going to say, okay, so the closest value, which is the 11, I want it to have a 1.5. A 1.5 movement, while the largest one, I don't want any effect on the offset. Okay. Then I'm going to go back to the offset curve, and I'm going to hide. No, I'm not going to leave this. And instead of offsetting all the curves in this example here, instead of offsetting all with the same value, now I'm going to be offsetting them with a proximity relation, right? So I'm going to connect the mapped values here to the value in the negative. And once I do this, I'm going to go back and hide the centroids, hide those curves, hide the point, but leave. Yeah. So you're going to see that the closer we are to the point, the higher the offset we have, and the further away we are from the point, no offset is being done, right? So if I move this point around, you're going to see that the whole grid is being offsetted, right? So probably 1.5 is a little too much, so let's just stick to 1. And then I'm going to hide in this. So whenever I move this, all the curves respond to the proximity of the point that I created. Okay. So I actually, if you go back to the extrusion, to to the mesh that we created, we want to actually have this mesh to be extruding, right? Not on the full plot, but on the offsetted curves that we just created. Okay, so instead of connecting those curves to the original grid, I'm going to be connecting those to the offsetted grid. So I'm going to move this a little bit to the left, to the right, this to the left, and then I'm going to take curves, and then I'm going to connect them to the move. And then you're going to see that everything now is updated based on the proximity of the point. Now, if I move it, it's going to be a little bit heavy to compute, which is understandable because you're going to see here that actually this component is taking a lot of time to compute. Okay. One last thing we need to double check. We need to double check that the number of curves that we have here, because since we changed the curves, are the count that is being generated, right? We mentioned this earlier before. But since now we have 47 different curves, we need to actually update this to 47. Then I'm going to click OK. Then I'm going to right click, and then randomize. And then you're going to see that all of them are being random. Perfect. So going back to the steps that we're creating. So we've managed to create the grid, we've managed to create the design that we have, we've managed to create the behavior that we want in the design. What we want to now is actually to create the analysis part, right? So what we're looking for is 3 different things, right? So as mentioned earlier, going back to the main plots that we have here, I'm going to move them here. So grid A. So we want to have maximum shade on this public space. I'm going to type in. So we want to generate shade on this public space, right? This is the first objective. The second objective is we want to reduce the amount of radiation exposed on the buildings, right? But we also want to maintain the highest possible square footage of those buildings, okay? So let's create those objectives. So the easiest one is actually the area. So since we have here the geometry, I'm going to hide this for a second. Since we have here the curves, right, I can easily just type and then connect this to the geometry, which will give me here a list of areas. So if I do this, so this is the area of each of those floors, right? And since I total area, something called mass addition, which essentially calculates the addition value of all the items inside one list. Okay. So I'm going to connect this to the input, but I don't want to maintain any tree structure because I want to have the absolute value of the total area of the whole project. Okay. So if I right click and flatten this, it will disregard any tree structure in the data generated, and will just give you the utmost total area. So, and then I'm gonna show again what we have, and then we're gonna move into Ladybug. So, Ladybug is an environmental plugin, and there are a lot of data on Ladybug online. Also, there are a lot of example scripts in their webpage. I think I'm going to share this site with you. And it's pretty straightforward. And the process of Ladybug is actually, you don't change it. You just change the geometry, but more or less everything else stays the same. Okay. So the first thing we want to have is we want to import an EPW file. Okay. So this is where the data gets collected from an EPW file. So in order to do this, you can go to the import, and then you can go to the EPW map. Okay, and then if you double click and click a button and connect this to the EPW map and click on it, it's going to open a web page. Okay, and this web page has all the location, well, most locations with the weather file within. Okay, so I'm going to click on one of the files, then I'm going to click on download DOE, then I'm going to have the file here, right? And then I'm going to go to this folder, extract the file, and then when you extract the file, you're going to see that you have 3 different files. What we're looking for is the file that is .epw, or in the type, you see here the EPW file. Okay, so we're going to go back here, and if you look at the input, it needs the file path. So I'm going to type in file path, right click, set one existing file, and then I'm going to go through the existing file, type on the EPW, and click open. Okay, so if you hover the cursor, you're going to see here the data that the file is successfully connected. Then I'm going to connect this to the EPW file. It's going to take a second, and then it's going to turn into light gray, which means that the component is working properly. Okay, so this is the first part. Next, we want to do 2 different things. So we want to analyze the radiation, and we want to analyze the direct sun hours, right, to check the shade and shadow. Okay, so we're going to start with the direct sun hours. So in order to do the direct sun hours, we're going to need to have another component called sun path. Okay, so we need to have first the sun path so that we can be able to calculate what is the direct what is the sun hours being exposed in this plot. Okay, so in order to do so, I'm going to connect location to location. So the Ladybug plugin is actually pretty straightforward. Whenever you see an underscore before the component, this means that this is an important component that we need to connect. And it's not that complicated, because whenever there's an input here that needs to be connected, you're always going to be connected to the output that is coming from the EPW. So if I see location, I just connect location to location, and so on. Whatever data that is missing here, I just find it here and then connect. And you're going to see this also in the next example. So once I connect the location to the sun path, you're going to see that the sun path is already going to appear, right? And this is the city where I'm at, Barcelona, or I want to select it. And then this is the path of the sun in this location, okay? The second question that's going to be asked, which is HOIS, which is hour of year, I guess. I'm not really sure. So if you go to the analysis here, you're going to see that here you can calculate the hour of year, okay? So if you get this here, so I'm going to move this a little bit to the side. Specify which month, day, hour, or minute that you're actually looking to analyze, okay? Since we want to have an overview, so let's say I want to have 4 different months. So let's say I want to have 3, June, 9, and 12, right? And then with Shift, I'm just going to connect all of them to the month, right? And then the day, let's say I want to select the 15th day of each of those months. right? Then the hour, let's say I want to have a morning, midday, and an afternoon hour. So let's say 8, 12, and maybe let's say 15. And then I'm going to connect again. Let's shift to the hour. Okay. Now, if you take a look at the data coming out of the hour of year, you're gonna see that we only have 4 different values, and that's it. It's because we have 4 different months, right? But this is not what I'm looking for. I want each month to give me 3 different outputs of each of those months, right? Because I have 1 day, so I want on March, I want 15th of March, I want 3 different values, and I want 15th of June, 3 different values, and so on. So in order to do this, I'm just going to right-click on month, and I'm going to type. And when I graph, it's going to try to match each of those, put each of those data on a branch on its own, and then it's going to take this branch and match it to the rest. So instead of having 4 different outputs, if I graph this, I'm going to have 12 different outputs, which is exactly what I'm looking for. Then I'm going to connect the HOI, H-O-Y, to the HOIs. And when I do this, you're going to automatically see that points are going to be appearing on the graph that I generated, right, on the sum path. So those are the points of the specific dates and time that I generated. And if I change the time, you're going to see that the points are being moved in time. So 18. Okay. So another thing that usually it might be an error that you usually might encounter: center, point, and the scale, because sometimes this sum path is a little bit way too big. So maybe you can have 2, then you can add it to the scale, and then you can control the scale of this diagram. And also the center point, if your building is not, so the center point here is already assumed to be the 0, 0, 0 of the Rhino model, but if the geometry that we is not in the center, then we need to specify a center point. So you can easily do this by going back to the surface we generated, the big surface, and then type in area to get the center. And then connect the centroid to the center point, and then you're going to see that the sum path is going to update its location to the newly generated center point. Okay, so now that we've generated the sum path, we want to actually do the analysis, right? So this is only we're preparing for the analysis. So if we move on to the direct sunlight analysis, you're going to see that one of the main inputs is actually the vectors, which is the location of the sun. So I'm going to take it from the sun path and connect it to the vectors. Okay, it's going to ask for a time step. It's fine. If you right-click on the orange bubble here, it tells you what data is actually missing for this component to work properly, right? So when you click here, you're going to find that it's missing geometry, grid size, and the run. Okay, so what is the geometry that we're trying to analyze? So again, we're trying to analyze the public space to have the maximum amount of shadow possible, right? So we want to analyze now what is the amount of shadow generated inside this space. So this means that this is the geometry that we want to analyze. So I'm going to connect this to the geometry. Okay. The second question would be, okay, what is the context affecting this geometry, right? And the context that we have is the meshes, right? The buildings that we generated. So I'm going to connect the meshes to the context. Then I'm going to check again It's going to ask for a grid size. So let's say the grid size is going to be 2. Be careful with the grid size, because if the grid size is too small, this component is going to take a lot of time to run, because the smaller the grid size, the higher the resolution of the analysis is going to be. And then for the run, if you hover the cursor over the run, it's going to tell you that it needs a set of true or false, which is an on or off toggle, so that this component can run. It's like a phase switch. So I'm going to type in Boolean toggle, and then I'm going to connect Boolean toggle with run. And once I do this, you're going to see that the component now is working properly. It's false, so I'm going to double click to change it into true. And then once I do this, this is going to pop up. So you're going to see again that there's a little bit glitch in the view. This is because some surfaces are being overlapped. So if I go back and hide this, you're going to see that this is not any more glitchy. So what is happening here is that the direct sun hours component is generating a gradient of colors starting from 0 hours to 9 hours, right? So this means that during those points where the sun is going to be, where the sun is located, which I specified earlier, those are the locations where we're going to be that are going to have the more exposure to sunlight, and the bluer it gets, this means that the less sunlight is going to be exposed. Okay, and if I decrease the grid size to 1, you're going to see that the resolution is going to decrease a little bit. Okay, so increase. So this means they're going to have a more accurate overview of what is happening. Okay, so this means that if I go back right here and I change the value of the extrusion, you're going to see that this grid here is going to be changing. So if I right click and I randomize this, you're going to see that it's being updated based on the extrusion of the different buildings, right? Also, if I move the point, which is the scaling factor, it has a huge impact on the shaded part, which part is going to be shaded and which part is not, because it's creating openings between the buildings. So the further it gets from the part that is exposed most to the sun, is going to be acting as if it's a wall, which is going to create a stronger shade inside this area. Perfect. So I'm going to go back. Now that we have this part covered, we can actually change the color of this gradient. So there's something here in the extras called legend parameters, okay, which can change the color of the analysis being generated, right? Because this is shade and shadow analysis, so maybe it makes more sense to have it grayscale, right? So in most of the components that you analyze, there are a component called legend parameter. Then you can connect legend parameter to legend parameter, and then if you go to the extra, there's a color range, right? And if you hover the cursor over index, it's going to give you a list of all the default values that are being generated inside this color, right? So if you look at number 5, it's called shadow study. So if I type in 5 and connect colors to colors, you're going to see that it changed into a shadow study, right? It's just changing the colors. You can also move this and it's going to generate different types of colors. But for now, let's keep it at 5. So that we know that this is the shaded part. This is more part exposed to the sunlight. Okay, moving on to the second part, which is we want to analyze the radiation of the buildings, right? So in order to do this, we're going to have the radiation. The radiation is going to ask for. So if you go back to visualize, you're going to see that there's a Ladybug cumulative sky matrix. So we drag it here. It's going to take a while. Now it's connected, and then we're going to go back. So Going to go back to the main component, which is the import EPW, and then it's going to need a location. So I'm going to connect location to the location. Then it's going to need a direct radiation. So if you go here, you can see direct normal radiation. I'm going to connect this here. It needs a diffused radiation. So here you're going to see diffused radiation. I'm going to connect it here. And then it's going to need, again, the hour of the year, right? So I'm going to use the same hour of years as we're using up there. Okay, and then you're going to see that the component is functioning properly, right? Then I'm going to do the same as I did here. So I'm going to connect sky matrix to sky matrix, and then I'm going to check what other inputs that I need to connect. I need to connect the geometry, grid size, and the run again. So the geometry that we're testing right now is the buildings, right? So I'm going to go back, take the mesh of the buildings, and then I'm going to connect it to the geometry, right? In this case, we don't have a context because the context is actually the buildings themselves, because the buildings are going to throw shade on each other. So this means that the radiation is going to be affected by other buildings. So we don't need actual context. If you leave it empty, it's fine. It's going to assume that the geometry is being analyzed upon itself. And then the grid size, again, is to 2. And then we need toggle, so I'm going to connect this to the run. It's going to take a bit. So what happens here is you're going to see that there's an error, right? And this error is because actually the meshes that we're generating here, they're open. It's just a wall. So if I hide this, you're going to see that this is not a volume. It's just an outer surface. So what we actually want to need from this extrusion is actually to cap holes so that we can transform it into a B-rep. So it's a solid geometry, and then connect this B-rep to the simple mesh. It's going to take a second. And then if I hide all this, zoom out, now it's working properly. Okay, so now you can see the amount of radiation being exposed on each of the floors of the buildings, right? So it makes sense that the buildings towards the highest or the noon are going to be exposed most, while the buildings from the inside are going to be shaded the most. Okay. And again, if I go back, randomize the value, take a little bit of a second, and then you're going to see that everything is going to be updated, right? As also, if I move the point of scaling a little bit, everything is going to be scaled, everything's analyzed accordingly. Okay. So after this analysis, there are 2 things we need to get, right? Which is the most important part, which are the results. So if you go and type in data, connect the results here, and then type in panel. So those are all the results of the buildings that we have, right? So this one is for the public space. So this is for the grid. So each grid has a certain value. And then if I type in data again here, and then connect this here. So this is the radiation result for each of the floors of the building. Okay. So again, the purpose was we want to, let me change this to shade shadow. And I'm going to change this to radiation. So what we want to do is we want to have, I'm going to do a mass addition. Connect this here, and then connect this here, right? So I want to have the maximum shade, right? So if you take a look, maximum shade is actually the lowest value, right? And if you take a look at the result, this is the result that we have, which is 3,934 hours, right? So we want to have the least exposed hours on this part, while in the red, I'm going to do again mass addition to the radiation and get a result. And also, we want to decrease the amount of radiation on the buildings. Okay, so this is really important. So I'm going to type in scribble, and I want to minimize the radiation. Actually, shade and shadow is actually misleading. It's sunlight hours. So I want to have the less sunlight hours as possible, because this is what's being calculated, right? So I want to minimize the sunlight hours, and I want to minimize the radiation, right? And then I'm going to go back, and then I'm going to take the area. So I'm going to type to the result, and then I'm going to type in here total area. Then I'm going to take this here. And I don't want to minimize the total area. I want to actually maximize the total area. So now that we're done with the analysis of the situation, let me go back here. So now we finished the analysis. Now we want to connect this analysis to the optimization and run it through Galapagos. Okay. So in order to do that, because Galapagos is actually a single objective solver, I'm going to type in Galapagos. This means that Galapagos can only deal with one value. Okay. So there are multi-objective solvers like Wallasey, for instance, and Wallasey can deal with multiple objectives at the same time. However, it's a little bit complicated to use. So right now we're going to use Galapagos, but Galapagos needs just one fitness. What does this mean? What does mean one fitness? It needs just one value to control. Okay. So going back to the slides, we specified that we have here two different things that are being used in the solver, right? The genome, which are the design variables, and then the fitness, which is the objectives or the analysis. Okay. So if I go back here, you're going to see that those three are actually the objectives, right? The sunlight hours, the radiation, and the total area. But they are three different objectives, and Galapagos only deals with just one number. So this means that I need to formulate some sort of equation between those three to just give at the end one value so that I can connect it to the fitness. Okay. So in order to do this, we want to minimize the values, right? So let's take a look at Galapagos. So in order to enter Galapagos, you need to double click on the icon, and then this new window will pop up. Okay. So Galapagos is it has two different solvers inside of it: evolutionary solver and annealing solver. Usually we're using evolutionary solver. It's the most accurate out of them, and the fastest actually. So we're going to only be dealing with evolutionary solver at this point. So those are the first options. So here you specify the different options, and then you move on to the solver, and then you start computing the different iterations, and we're going to go over this in a sec. So for the options, here you have the fitness, right? And as also we're mentioning the same, this is the fitness, which are the objectives that we're looking for. So there are only two options, either minimize or maximize the fitness, which means that it's either going to try to minimize the value that we have here. So if I connect the fitness to the total area, this means that its only objective is going to be dealing with the total area of the buildings. right? So if I double click here and choose maximize, then this means that the solver is going to change all the parameters in the design so that it can get the total area, the highest value possible, right? The maximum value possible. If I change this to minimize, then this means that it's going to change the parameters in order to get the minimum value possible. Okay. So what I want to do is I want to create an equation. Okay. So if I want to minimize those two, I can just simply multiply or addition. So I can just multiply this and that, or I can just type in addition, right? And then this means that the result that I'm looking for, let's type in data. And I can just connect the fitness to the data. And then this means that I can double click here. And since I want to minimize both data, right? So it's pretty straightforward. I just need to go in here and then transform this into minimize and click on the solver to store, okay? But since I want to have one data to be maximized while the other being minimized, then we use this trick. If you go into the mathematical part, you go to this part, then you go to 1/x, okay? And then you connect a value. So let's say that I want to have a value of 2. Then I'm going to create a panel. Okay. So if the value is 1, it's going to give you a 1. If the value is 2, it's like 1/2, which is half. And the higher the value it gets, the lower this number gets, right? So in a way, if I want to increase this output, I need to minimize this output. Okay, it's a little bit complicated. So if I have here, if this is 1, you're going to see that the output is 1. But the more that I increase the output, which is the area, the more the area is increased, the lower the value is being presented, right? And since I want to minimize all the different inputs, so I actually want to have this reverse operation, right? So I want, the more I increase the area, the better it gets, which gives me a minimum value. So I'm going to go to the multiplication, add a plus, and then I'm going to connect the result to it. And then you can see it here, right? So this means that if the area is low, it's going to give you a higher value, which is not what we're looking for. We want to minimize this, right? So this is the total value, the total evaluation, total fitness. Okay. So if the area is low, then this number is huge, which is not what we're looking for, because we want to minimize this value as possible. So this means that the solver is trying to get the area possible so that it can minimize the total fitness. So I'm going to connect again total area to the value. I'm going to delete this. Then I'm going to put it here. Okay. So let's go back to Galapagos and let's explain a couple of things. So because Galapagos can actually run for days nonstop, and it's actually going to consume a lot of your computation power on your PC or laptop, sometimes you need to have a threshold, right? Threshold is like a value that you add. If you have your cursor here, it's acceptable fitness. So you can say, okay, if this value reaches, if I go back here and check that the result that I'm having is 1,540, and let's say if this result reaches 120, then this is it, stop calculating, right? So this means that here you can specify a specific value, or you can just leave it open to maximize or minimize the fitness. Okay, so again, as mentioned, in this case we want to minimize, so I'm going to keep it minimize. You can also enable a runtime limit. Okay, so you can just click on enable and then tell it to run for maximum 1 hour 30 minutes, or you can specify whatever you want so that it's controlled. Okay, now In the evolutionary solver, this is usually what we're looking for. I'm going to put this here so also it can be readable. A second. So we have here 5 different things, right? The maximum stagnant, okay, which is the maximum value or the maximum amount that when the component is optimizing and nothing is being optimized, there is no optimized result, then it should stop. Okay, so the way the genetic solver works is it goes something through a population. Okay, so there are different generations, and each generation has a specific population, which is the population here is the 50. Okay, so it tries 50 different iterations. Okay, and then picks the best out of those iterations, and then moves forward to another generation. So it starts generation 1, generation 2, and so on. And each of those generations will have a population of 50. You can control the amount of population that you want. Okay, so the maximum stagnant is when it reaches 50 generations without an optimized result, then it should stop because it's reaching the best possible answer it can get. Okay, so it's also like a phase switch again. There's also an option with the initial boost, and initial boost is really useful if you have the model only has specific local parameter values combined with value combinations that lead to great results. So if you have different multiple parameters, in our case, we don't have a lot of parameters. We have 2 different parameters, which is the number of floors and the scaling factor. But if you have a lot of parameters, it's better to have a higher initial boost. And also if the setup of your script is not controlled, there are a lot of open-ended, like a lot of freedom in the design. It's also better to initiate, have this initial boost a little bit. Usually we leave it at 2, and you can feel free to play with it and experiment different values. Okay. The last 2 parts, which is the maintain and the inbreeding, maintains the amount of results that should be combined every generation to find a new better result. So 5% of this generation is going to be kept and then combined with the next generation. Okay, and the inbreeding is the freedom factor of the algorithm to use very similar or very different genes. So a high positive factor means that the algorithm will only use genes with very similar results. So the higher it gets, it means that it's not gonna experiment with different genes. And the lower it is, the more wild it's gonna get, and it's gonna experiment different genes. Again, this process is a trial and error. You can keep changing. Usually we keep the population 50, but let's do it for 25, and maybe we can keep this also as 25 or 30. Okay, and we want to minimize. Okay, so I'm gonna click OK, and then I'm gonna go back here to prepare the script. So the 2 parts, again, the genome and the fitness. So we already connected the fitness, but what are the genome? So if you go back and take a look, this is the part where we're controlling, right? We're randomizing the number of floors in each plot so that we can generate different values in the public area and the total built-up area, and also the minimum radiation, right? So this is parameter number A that we're going to be controlling. Okay, so the way the genome works is actually it works backwards. So I'm going to take this there. So what you need to do is you connect the genome, and when you click and hold, you're going to see that this DNA sort of icon is going to appear, and then you connect it here. You're going to see that this is connected to this part. Okay, so this is the first part that we're going to be controlling. Okay, the second part that we're going to be controlling is the location of the scaling factor, right? So if you go back here, you have the empty slide. So if If you come here and you connect this genome to this empty slider, it's not going to work, okay? Because genomes only work on sliders, like a slider like this, okay? So what we're going to change this into a slider. So if you take a look at the input here, it needs a coordinator, a UV point, okay? And this means that if I type in a panel, let's say 0.5, 0.5, and 0, which is corresponding to X, Y, and Z, and connected to the point, is going to give me the center point, okay? So what I want to do is I want to generate this 0.5, 0.5, and 0, okay? There are multiple ways to do this, one of which, if you want to construct a text panel like this, we use concatenate, okay? And this uses different fragments of text to select to have a result. I'm going to show you right now. So if I want to type in curly bracket and then 0.5, 0.5, comma 0.5, and then another curly bracket, this means that I'm going to type in, I'm going to copy this, and then I'm going to type this part. Like I'm exploding this text, and I'm going to connect it here, and you're going to see that this fragment starts like this, okay? And then what is the second fragment? The second fragment is a value. So I'm actually going to type in this, I'm going to put it here. So you're going to see that the one started to appear. And if I change this, this is going to be changing as well. If you zoom in, you can add different fragments, okay? And if you take a look now, we want to have this comma right here. So I'm going to copy this, have a comma, and then I'm going to connect it in A. Copy this, connect this in B. And then for the Z value, we wanted to keep it at 0. So I'm going to keep this 0. Then I'm going to take the comma, put it here. So basically, I'm just constructing the text, right? So that instead of, if every time I want to change, I'm going to double click this and type in manually what I want to have the value, which is 0.2 or 0.3 or whatever. I'm automating this process by having those values. So when I change, this changes, and then this can be connected to the point. Of course, there are multiple different ways you can construct this, but it's important to know how to type in a fragment in Grasshopper, right? And then the last part, which is we're going to close the bracket. So I'm going to copy this here, and then I'm going to change it to this. Okay, now that we have that fixed, and then I'm going to copy, I'm going to connect this result to the point. Give it a second, and now everything works fine. Okay, so this means that this is the X direction of the point. This is the Y direction. Then I can go back to the genome with Shift and then connect this and connect that. So now I'm controlling all the sliders with the genome. Since this is going to take a lot of time, which is the 2.7, okay, I think I'm going to maybe scale down this whole thing. And I'll go back and I will reduce the number of subdivisions that we have so that we have less objects to compute. Yeah. Now this is a little bit faster. And then since I changed thing. So I need to come back here and update the number of buildings that I have, which is now 30 buildings. Okay. Okay, so now that we have everything set up, it's time to start computing and running Galapagos, right? So what I'm gonna do is I'm gonna double click here, check everything is fine, minimize stagnant initial boost. Let's say the initial boost is gonna be just 1 since we don't have much variables, and then I'm gonna maintain 5 and 75%. Now, if you move to the solver, which is the second part, see this this bar, right? So this is the type of evolution of solver that we're looking for, right? Remember here we had an evolutionary solver and a annealing solver. So here you get to choose which one you want. So we're going to use the evolutionary solver, and then it's really important to check on the right. This is display. Oh, so this is the display value, right? So because it's going to keep on moving everything around, this tells you if you click on this, it's going to display every iteration being generated, which might take a lot of computing processing, right? And if you check the second one, it's only going to change. It's only going to preview here the better options. And the last one is it's not going to display any of the genomes, so it's going to run computing. You're going to see the values changing in here, but the display will remain the same. Okay. So right now I'm going to keep it at the better genomes, and then I'm going to start the solver. It's going to take a little bit of time. And you can see already it's generating different iterations, which is the first generation, the initial generation that we did. And if I actually change this here, you're going to see that it's displaying all the generations, everything, the points being moved, everything is being generated. So once we give this a little bit of time, this graph is going to start updating. Yes. So here you're going to be starting to see the different generations that we're having. Okay, so here is going to tell you the graph. So right now we're on generation number 0, so there's nothing happening. It's still randomizing different iterations, and you're going to see here that this is the wide varieties of option that are being explored, right? And then here you can see that these are the points that are being generated. On the right here are the different fitness values that are being generated. So those are the values. And then here, just a second, it's a little slow. And on the right, it will give you the best options, the best list of options to the parameters that are being selected. Okay, so you can, after the solver finishes, you can just click on the highest 10 or the highest, whatever highest one that you want, and then you can click on reinstate, and then it will apply this those parameters to here, because this is going to give you the best fitness. And when you click on each one, so what we're looking for here in this graph is actually for this graph to be averaged out, right? So now it's going up and down, and we want to have it more homogeneous, more averaged out. I'm going to show you also pictures on how this graph the optimum solutions should look like. as well as this graph. So what you're looking for is that each generation, when it goes, it reduces the amount of variety, right? So I'm gonna stop this solver right now. Sorry. Yes. So this is what we're looking for, right? So this is usually how the Galapagos editor usually looks like, right? So what we want to have is we want to average out those curves, right here, and then we want to have this curves instead of trying different parameters. So this is the wide range of parameters, and the 0, 1, 2, 3, 4 are the generations being generated after, right? So this means that with the evolution of the generations, it's getting to the optimum result, right? So the less this graph goes up, this means the more optimum the solution is getting, right? And then you can click here and then reinstate the parameters of those. So I can just click here, and if I click reinstate, it's going to go back and it's going to change this to the certain parameters that we have. So the last thing I'm going to say is that this is the complete process of the project till the part where you generate the design. You can essentially, which is what we did here, you can essentially use whatever design you want. You can use there are a lot of options online on YouTube with different designs. You can actually test this method with different designs. What you're going to need is the analysis part, which is how to analyze the design that you have, right? Which is, again, this part here. So whatever the design, you need to have this fitness, which is the analysis part, and then you need to know how to connect the fitness to the genetic solver. And I think this is it. If you have any questions. Sorry.
Thank you.
Yep.
Hi, Daniel. Thank you so much for an enriching tutorial. I think you've highlighted really key aspects and the workflow, which I think is really crucial, and the use of optimization as well, which I think would create an efficient and a smart design process. So thank you for that. Let me just check. So we have a few questions on the technicalities of the process, but before that, I'd like to ask you more general questions on, for students who are trying to venture more and dive deep into the computational design process, what do you recommend in terms of sources or references in the field just to help them advance in that?
Okay. I can actually share with you a couple of references. So give me a second. So if you, I'm going to share my screen again.
All right.
Okay. So actually, the website Grasshopper 3D is actually one of the strongest sites that you can actually check a lot of example files, And there are a lot of, if you click on Learn here, you can get to start. There are multiple books and online platforms that you can actually follow the introduction. For instance, this introduction by David Rubin, which is the guy who did Grasshopper, introduction to Grasshopper videos. And ModeLab is actually one of the manuals that actually explain a lot of, especially on the data management part, which I know that we skipped. It has a lot of very thorough explanation to Grasshopper. And if you want to have more in terms of like Ladybug analysis, there are also websites for Ladybug analysis with example files. So I think there are multiple options if you, and this is only Grasshopper 3D, and it's connecting to different multiple websites. So here you can find a lot of data that you can follow. The advice I would give is actually, because Grasshopper is, it's a language, right? It's like a programming language, and like any language in the world, you need to practice it. So I would highly recommend just following basic YouTube videos just to get your hands used to it, to the logic, to get used to the logic, to the concept of it. And the more you experience with it, the more you're going to face the problems. And then this is where you actually try to search for the problems and then understand what is going on. I hope I answered the question.
Thank you so much, Daniel. Yeah, I think that would be a great help to our students to just take a look deeply and to learn the how to find those answers themselves, which I think is an important skill. And I just want to check, Daniel, will you be sharing the code and the files with our students as well?
Of
that
course,
we worked on?
of course.
Okay,
of course.
Sounds good. Okay, I think we can start taking the questions. So one of our questions says, do we have to understand each command in Grasshopper in order to be able to create a process?
Not necessarily. I mean, it's important to understand how to read the script, to more or less understand the workflow of the script. Some of the components are maybe a little bit too technical, and you can complexify or simplify the process as much as you want, right? But the workflow still remains the same. So no, not necessarily. You don't need to understand each single component in the script, but you need to understand the general idea of why this part is being generated, so that you can understand the flow of the script, so that you can manipulate and control it more.
Absolutely, yes. I think this will also give them a general understanding on how to develop their own scripts by learning all of this workflow. Yes. We also have another question. Let me just. Oh, okay. So someone's asking, could you please explain the differences between annealing and evolutionary solver?
Sure. So I'm also going to share with you a link that's probably going to explain it better than I would, but just give me a second. Okay. Should I share the link in the chat directly?
Yes, please. That would be good.
Okay, perfect. Okay, so this link, it has a lot of the optimization about Galapagos, and you're gonna find more thorough, more thorough explanation to everything. Also, I'm gonna share the screen just a second. One more. I'm sorry.
No,
if you double click actually on Galapagos, you're going to find here that there are multiple links that you can click, and it's actually explaining more the theoretical logic behind each of this process, right? So if you want to dig deep and understand more what is happening inside Galapagos and inside evolutionary solvers in general, I would highly recommend to go through those links and take a look at them. Answering the question of evolutionary solver and annealing solver. Evolutionary solver, it deals with, so it creates generations, right? So you start with a generation, and then it takes the best solution in this generation and then moves forward from this solution and creates another generation, right? So if you take a look again at the graph that I showed, this is how it looks like, right? So this is actually the difference between the two. So each generation, it gets a little bit better while you're working, while developing, because it takes the best solution and creates another generation. Annealing does not work in the same way. Annealing is more generic. So it's just testing out generation, random population every time it goes. So if you have a problem that you're looking for an optimal solution, it would be better to use um, choose the evolutionary one, right? But if you're looking to more exploration rather than a question that needs answering, then annealing solver can be the better decision.
Yeah, I think you've answered that quite well, Daniel. Thank you very much.
Yes.
We have also another question. So they're saying that if there's a way to export to an Excel file, speaking about the results from Galapagos, just to manage and analyze and share the data involved with the process. So.
Yeah, sadly, with Galapagos, once you close the solver, the data is being generated, it gets lost. So there is a workaround for this problem, which is actually we record the data as the Galapagos is running. I have a script. I prepared the script for this part, but sadly we don't have the time to go through. But I can share the script to record the data and have it with you, so that whatever process that goes through Galapagos, it's stored in the Grasshopper file.
Yeah, Daniel, will you be sending the script through the chat here, or do you want us to forward it to the students?
I think it's going to be better to forward, because I'm going to tidy up the script a little bit and then maybe give it, and then you can forward to the students.
Sounds great. Okay, I think we had an earlier question which I wanted to keep in the end as well, because I'm sure some of the people who are watching this here today are also students. Some are aspiring to do their masters as well. So someone was asking, what are some of the recommended computational design postgraduate program that you would recommend for students who want to venture in this field?
Well, it depends. Sorry.
As if you would want to also highlight the program you've worked in with and how it helped.
Yeah, it's really important to understand the different subtopics inside the computational and then inside the big topic of computation, which is something that I was exposed to when I got actually to IAAC. So I studied at IAAC. I did a master in Advanced Architecture, which is a general master that covers a wide variety of topics, which I highly recommend. If you do not know exactly which topic that you're looking for, it's better to have a broader look on different topics. So they cover topics of the digital fabrication, robotics, a little bit of digital sensing, algorithmic design. So it's important to before jumping in and picking which programs that you want. It's important to take a look at the different topics and actually pick what you actually are interested in, and then you can check which program is best. But I would recommend, if you're not that informed about the different topics, then it's important to have something that is more generic before specified.
Yes, absolutely. Thank you so much, Daniel, again. I think also other people are asking about the workflows in the files. So like we've said in the chat, all the files will be shared through email. That was you guys used to register with the session. So you'll have this, and the tutorial was also recorded on YouTube. So all of this is available. So I don't know if we have any more questions. I think that's it with the questions. I just want to thank you very much, Danielle, for such an enriching tutorial. And I think you've opened doors to so many students and people who aspire to work in the field, and how to venture and you've taught them not just what is there within the computational field, but also how to achieve the outcomes they aspire to. So we're very happy with that. And I also want to take this chance again to tell everyone to watch out for our Instagram and social media for Digital Futures. We'll be having many upcoming sessions. Bhavleen, do we have anything else that we want to add at the end?
Yeah, I thought maybe it'll be good if students want to reach out to you, Daniel, sorry, in case you have any email or that
Of course.
you would want them to reach out.
Of course, I'm gonna share. I can also share this in the chat.
Oh yeah, that would be good. Yeah, that's it.
And I'll share the same with the YouTube participants as well. We have a very enthusiastic audience on YouTube as well today. Yeah.
Perfect.
All right. Daniel, is dropping your details in the chat, or do you want us also to send it to?
Oh, it's fine. I can also send it to you, and then you can forward it.
We can send those through email as well.
Okay,
all right.
perfect.
So for everyone, yeah, just feel free to reach out to Danielle as well. And like I said, I just want to announce that we have upcoming sessions on our Italian talks, which is our first session. So watch out for this. It's a range of really good international expertise in the field of AI computational design. And next week, we're having our very first session on AI, series on AI Midjourney, and our very first session will be taught by Professor Neil Leach. So make sure to watch out for that. And thank you everyone for joining today. I really hope everyone learned and enjoyed. Thank you so much, Danielle, as well.
Thank you so much. It's a pleasure.
Thank you, guys.
Bye, everyone. Bye.
Bye.